Let me just jump into this practice test. When I do this particular example, I should probably take any point that's marked, but the point's not written, and just write it down. I think it's going to help me. This first point that's marked with a solid circle is the point -2, +1. This point marked at the closed circle here is 0, 0. This is 0, 1, 1, 2, 2, 1, 2, -1, and 4, 2. I think those are all the points. I don't know that I'm going to need all of those, but I just marked them just because I usually give those to you. I used to not know how to make these graphs, and so I was limited to what I can find on Google Images, but now I know how to make them. So to do f of 0, I'm looking for a point that has an x-coordinate of 0 with a solid dot. So this point right here is called out in part A, and I just want its y-coordinate, which is 0. For f of 1, I go to 1 on the x-axis, look for a point marked with a solid circle that has an x-coordinate of 1 and its y-coordinate is 2. The answer is going to be 2. If I went to f of -2, I look for the point that has an x-coordinate of -2, its y-coordinate is 1. Every now and then, I would ask this question, let me Hij, K. If I asked you to find f of 4, I'd look at x equal to 4. There's no point marked with a solid circle. F of 4, if I asked it, which I didn't on this particular test, but it would be this particular practice test, it would be a DNE. Every now and then I sneak one of those accidentally on the test, forgetting there isn't one of these on the practice test. But f of 4, since there's no point that has a solid circle marked at 4, would be a DNE. Now for limits, I need a left-hand limit, a right-hand limit, and a two-sided limit. And because at x equal to 0, the graph goes in and out the same point. So at x equal to 0, the graph goes in to the point 0, 1 and out from the point 0, 1. All three of these will be the same. D, E, and F will all be the same. Even though there's this stray point marked, it has nothing to do with the limit. My graph at 0 goes in and out from the point 0, 1. All three of these are going to be the y-coordinate of that point. It's when the graph goes in from the left side, one point, out from the right side, another point, then I get different values. But all of these, I go in and out that point. That point has a y-coordinate of 1. So this is kind of my in. This is kind of my out. The in is the left-hand limit. The out is the right-hand limit. For problem G, it's calling 2. And here's 2. This is my in. This is my out. It goes in and out at x equal to 2. It goes in the point 2, 1, and that's for the minus limit. Out from the point 2, -1, that's for the plus limit. They're all going to be different, and the last one's a DNE. So the left-hand limit's going to be 1, because the left-hand side, it goes in to the point 2, 1. It comes out at the point 2, -1. The right-hand limit's going to be -1. And when these two aren't the same, the two-sided limit is DNE. So this is the point for the minus limit. This is the point for the plus limit. Graph goes out for the plus limit, in from the minus limit, and I'm looking for x coordinates of 2. Both of those have 2's. And I want the y coordinates. Limits are always y coordinates. And if the left limit and the right limit aren't the same, or if the minus limit and the plus limit aren't the same, this is a DNE. Next, we're doing limits at infinity. And there's two kinds of problems. There's one where I mark a dashed line, a horizontal asymptote, and this is the positive infinity side. This is the negative infinity side. Both the side of the graph that's towards positive infinity and the side of the graph towards negative infinity both go through this dashed line at 2. So both of the limits are going to be 2. The right-hand limit, or the positive infinity limit, and the negative infinity limit are going to be 2. It's conceivable, it's harder for me to do, but it's conceivable that you get a graph like this on the test that has 2 dashed lines. If this was the graph, this is going to be for the minus infinity limit, this is going to be for the plus infinity limit. If this was the graph, part A, the limit as x goes to positive infinity is the y coordinate of this dashed line, which is -3. And for part B, the limit as x approaches negative infinity is the y coordinate of that dashed line, which is 2. That every now and then I sneak that on the test, just like every now and then I put that DNE for part 1, so I just wanted to mention it. The next limit at infinities are for graphs that don't flatten out. And when you don't flatten out, so this is limit at either negative infinity or positive infinity. If it doesn't flatten out, then your answer is either positive or negative infinity. This is the positive infinity side. This is the negative infinity side. This is going lower. This is going higher. The positive infinity side is getting higher. It's going towards the top of the y-axis. So on the positive infinity side, this would have a limit of infinity. On the negative infinity side, the graph is going down. It has a limit of negative infinity. I could do something like this. Ask the same questions. If I ask this one for part A, it's going to be the same limit for the positive infinity because it's going up on that right-hand side. This is the positive infinity side and it's going up. So the limit as x approaches in positive infinity would still be infinity. But for part B, the limit as x approaches negative infinity, which these are the negative x's, it's also going up as opposed to going down. This would be another positive infinity. So I look at the right-hand side, that's for the positive infinity. If it's going up, it's positive infinity. If it's going down, it's negative infinity. Then I look at the left-hand side for the negative infinity limit. If it's going down, it's negative infinity. If it's going up, it's positive infinity. So this isn't the only variation of these graphs. You just have to know left side and right side. Left side is the positive infinity. Since these are going up, they're both positive infinity. Right side, or left side, if it's going down, it's negative infinity. Going up, it's positive infinity for the negative infinity limit. Negative is barely readable there. Now some finding limits by algebra, and I'll be efficient and not do everything that I might do. I'll just do what I have to do. And for question 4a, it's finding the limit of a polynomial at x equal to 2. I can do that by just plugging in 2 for x. In fact, for any limit, it's proper to take the given value of x and plug it in. And if you get something other than undefined, that's what the limit is. The answer to part A is going to be 9. I usually don't put those on the test, although it would be nice if I did. The next few problems are limits of fractions, and while I should technically plug the number in, I can promise you, unless I messed up on my writing, I'll get 0 over 0 if I plug the number in. So for the two fraction limits on the test for part 4, I should factor, cancel, and then plug the number in. Even though I can plug the number in at the start, it's gonna be a waste of time. I'm gonna factor, then cancel, and then plug the number in. So for part B of number 4, it's easy factoring. I'm not going to explain the factoring. Come visit me if your factoring skills need some brushing up. But hopefully, if you pause the video, you can figure out how to factor this if I give you enough time. In fact, when you're doing this video, you should have probably tried to do the whole practice test ahead of time and just be watching the problems that you didn't match my answer. That's probably ideal, rather than watching me do everything and possibly say something that confused you when you weren't confused to start. So, to find the limit for this fraction, I factor both the numerator and the denominator, cancel the x plus 2's, and now I can plug the number in. And when I plug the number in is when I stop writing the word limit. Simplify the numerator and the denominator. The answer to part B is 1/4. C is ugly. Again, if I plug the number in this case, if I plugged 49, I'd get 0 over 0. This is a bad problem. To get the limit, I need to multiply by the numerator with the sign changed. The numerator with the sign changed over the numerator with the sign changed. I FOIL and simplify the numerator. But I leave the denominator alone. So I'm going to multiply numerator and the denominator by the numerator with the sign changed. And that's going to give me the limit as x approaches to 49. I'm going to leave the denominator alone, x minus 49 times the square root of x plus 7. And up here I'm going to write what the numerator simplifies to. I'm going to FOIL the numerator. So I'm going to do firsts are square root of x times the square root of x. That's just equal to x. Anytime you multiply two identical square roots, it will simplify to what's under the square root without the square root symbol. My outers are square root of x times 7, which is plus 7 square root of x. My inners are minus 7 times square root of x. That's minus 7 square root of x. And my lasts are minus 7 times 7. That's minus 49. Outers and the inners cancel. And what the numerator reduces to is x minus 49. The reason I don't multiply out the denominator is so I can catch this reduction of x minus 49s, because what's left in the numerator cancels with that factor in the denominator. I can't write the numerator without without something, so I'll leave a 1 behind. And when I do the canceling, I don't need the denominator. I don't need the parentheses around that denominator that's left. Now I'm going to plug in 49. And get to my answer of 1 over 14. I'm going to change 5a because I know what I always put on the test, and 5a is more complicated than what I put on the test. And sometimes when I put an easier problem, then the students mess it up. So let me change 5a to something easier, to something more like you'll see on the test. While the problem there is fine, it's more difficult than the test. On the test, I almost always give this for the problem. And the difference between this problem 5 and the problem 4 is the limits at infinity. To find a limit at infinity for a fraction, you look for the highest power of x, in this case it's just x to the first power, and I multiply every single component of the problem by 1 over that highest power of x. So I'm going to multiply 3 over x times 1 over x. I'm going to multiply 6 times 1 over x. I'm going to multiply 5x times 1 over x, and minus 7 times 1 over x. The first piece in the numerator and the first piece in the denominator, the x's are going to cancel. I'm just going to be left with a number. The second pieces in the numerator and the denominator are going to turn into fractions. So this is going to be the limit as x approaches infinity of 3 plus 6 over x over 5 minus 7 over x. Once you get the problem rewritten so that every single x is buried in the denominator of its own fraction, then you can plug in infinity. And when I plug in infinity, I stop writing the limit symbol. So this is 3 plus 6 over infinity divided by 5 minus 7 over infinity. And calculus tells us that these pieces with infinity in the denominator are essentially 0. So this is going to be 3 plus 0 over 5 minus 0. And the answer to this problem that's made up, not the problem that's on the screen that I didn't do, is 3/5. That's more like what you're going to see on the test. If you wanted to try the 5a that's on here to see that you can get an answer of 4, go give it a go. And if you can't get it, visit me and I'll do it with you. And I feel like making an executive decision here. I've never put a problem like 5b on the test, so I am, been a long day, which might be for your benefit. I can't ever remember putting this on the test. So I'm going to skip this, and you can safely skip this. If you want to ask me in class, hey, is something like 5b on the test? I won't remember saying this, and then I'll have to look at the practice test, look at 5b, and I'll go, oh yeah, that's not on the test. But if for some reason in the future I change it, then I will update this video. But I can't ever remember putting this on the test, and I've been teaching brief calculus for a lot of time. And your note card only has so much real estate, so I don't want to clutter it up with stuff that you don't need. I don't want to try to confuse you any more than I have to. It turns out that chapter 1 is kind of on an island, and it's not really necessary for the rest of the class, and it's kind of the theory portion of the class, and so we can maybe take it a little bit easier than we might later in the semester. The next problems are from section 1.3, and in section 1.3, when we were given graphs, we were asked to find not only where the graph wasn't continuous, we were asked to find the reason. I don't ask you to find the reason on the test, I just ask you to find where it's not continuous. And this graph, maybe it's not showing up great, but hopefully good enough. As I draw on this graph, I draw a left half, then the graph has a break. A middle half, the left quarter, one middle quarter, the second middle quarter, and then the last quarter. So this graph has 4 pieces, a left piece, a middle-ish, and right piece, and each place where I stopped drawing is a place where the graph isn't continuous. I just need to find that value of x. So there's going to be this part where the graph has a break would be a reason 2, but I'm not doing reasons. This part and this part. There's 3 values of x where the graph is not continuous. I need the x coordinates of each. The first one I circled has an x coordinate of -3. The second one I circled, it's so hard to see, that's the point 1, 2 right there. This point that I circled has an x coordinate of 1. And the last points that I circled have x coordinates of 4. Those are the 3 values of x where the graph is discontinuous. If you wanted to give reasons, this is a reason 2, it goes in one point, out the other. This is a reason 1, there isn't any point with a closed circle mark there. And this is a reason 3, it goes in and out the same point, but there's a point with a solid circle that's different than it. But this is all you're going to be required on the test, just to scan the graph and look where the breaks are. There's a break at this point that has x equal -3, a point break there at x equal to 1, and a point there at x equal 4, the breaks. That's all you're going to be required to do. Don't have to give me the reasons. Last 2 problems are from section 1.3 again. Gives me a fraction, asks me to find where it's not continuous or where it's discontinuous. You only have to answer the x values. You don't need to give this extra verbiage here. So to find where a fraction is not continuous, the algebra is always to ignore the numerator. That doesn't give me anything about continuity. I solve the denominator equal to 0. And these are going to be the values where the graph is not continuous or it's discontinuous. Because it's a square, I'm going to factor. And again, I'm hoping that your factoring skills are good enough that since I'm not explaining factoring, that you could factor it. If you can't factor, then come visit me and I'll try to teach you factoring. Or come visit one of our great tutors and they can teach you factoring. But anyways, if I'm given a fraction, I'm asked to find where it's discontinuous, the values of x where it's discontinuous. Ignore the numerator. I set the denominator equal to 0. Because this denominator has a square, I need to solve by factoring. And I do the algebra to find the values of x that I need for my answers. So the answer for 7a, no reasons necessary. This graph would not be continuous or be discontinuous at -5 and 1. Turns out for both of those there's asymptotes there and it would be a reason 1, not necessary. The very last problem before we move on to part 2 is finding where that graph was discontinuous. And since it's not a fraction and it's not a piece function, since it's not a fraction and it's not a piecewise function, I'm probably going to spell this like a moron. I think that's how you spell piecewise. We did those in section 1.3. Since it's not each, it's continuous everywhere and there's no algebra. If you do any algebra, you'll likely find an x-intercept, but not a place where the graph has a break in it. So the answer to 7b, it's continuous everywhere. I don't usually put those on the test, I don't think, but it seems to me like I have in the past put those on the test. Maybe they bip on and off the test, so I was afraid to skip it. So that's everything for the first half of the chapter. The algebra in the second half is going to be a little bit more than this, so but it shouldn't be that bad if you just kind of just take it slowly. So let me stop this and we'll continue with section 1.4 or the rest of the practice test if that's what you're doing.